All right, here we go. Part 3. So there's a really valuable tool that we use in physics and in engineering called the free body diagram. Okay. And in a free body diagram, what you're really doing is you're making your object as simple as possible. You're reducing it to a single point. Okay. And then you're going to take all the forces that are affecting your object and you're going to put them on the simple object, the simple point. Okay. So it works like this. Okay. So here's a dog. All right. And what we want to do, we want to look at the dog and we want to say, okay, let's make a free body diagram of the forces acting on the dog. Okay. So let's start. It's good to start with the low hanging fruit, which, the easiest things. And so we're going to have some weight. All right. So the dog's got some weight just like that. All right. Okay. Then we got to look at our contact forces, our normal forces. And so we've got a paw here. There's a normal force. I got a paw here. There's a normal force. And all these should be straight up. So let me call that N1, N2, and N3. Just like that, okay? Then we're going to have one more force that we're going to deal with, and that is the tension right here, coming from the rope there. Okay, now what we want to do is we want to transfer all of these to our free body diagram. All right. And so again, start with the easiest one. So we're going to move our weight over here, just like that. There's my weight. Okay. Now, these normal forces, okay, most of the time, at least for where we are right now, it doesn't matter that we've got N1, N2, and N3, but technically we have N1, 2, and N3. What matters mostly is that these things all combine together to create an N value, okay? And so I'm going to combine all those into a single vector on my free body diagram, all right? And then finally, I'm going to put the tension on here just like this, okay? Now the tension's on there at an angle, and so we want to kind of make a note that we can think of having components. There's a TX, and here's a TY, just like that, okay? Now if we think about the lab we did where we had the tabletop and we put some weight down here, we put some weight down here, and we had to figure out what goes over here like this. That was an equilibrium situation. So all of our forces balanced out. So we know if we looked at how much we had here that had to match to the left, how much we had up had to match going down. So the components of this guy at an angle had to match the other two pieces. All right. Ooh, I don't want to get rid of all that. Just kidding. Okay. So let me get rid of this. Boom. Okay. Yeah, I got rid of too much. Too much. Got to bring that TY. Hey, there we go, TY. Okay. Now, if you look at what we have right now, and you imagine that we had a ring here, and the ring's getting pulled up by N and down by W and at an angle by T, you can see that ring's not going to float, is it? Because there's nothing, sorry, in the video it's this way. Okay, there's nothing over here this way. Okay. Well, turns out we have forgotten that there is another force acting on the dog, and that force is going to be a little bit of friction here. Oh, I got the wrong tool. Sorry about that. I've got a little bit of friction here. So that would be an F1. A little bit here, we call that an F2. And a little bit here, F3. Okay? So those are pushing forward. Now, here's where it's a little bit tricky. Okay, because when we're walking, I mean, we can imagine the dog, and we imagine the dog pushing back, right? We imagine the dog pushing back. All right, but what's really happening there? Here's the dog's paw, here's the concrete, and the dog, when it pushes back, its foot is going to try to slide across the ground. You can imagine if the dog were walking on ice, its foot would just be like, woo, just like that. So what's keeping the dog's foot from just spinning out like that is the friction pushing it. Okay, so the friction is opposing this sliding. The sliding is this way, therefore the friction is this way. Okay, just like that. So the friction acts on the dog's feet to propel it in that particular direction. All right. Now, you may need to spend a little bit of time thinking about that because we're so used to thinking from our perspective. But what we have to learn to do is we have to learn to think, what's happening to the dog? Not what the dog is doing, but what's happening to the dog. All right. So what's happening to the dog is there are normal forces up on the dog. There's the tether creating tension on the dog. And then there's friction pushing forward on the dog's feet. Okay. So if we draw our friction here on our free body diagram, and again, we don't need to worry about F1, F2, and F3. They're going to combine together to make a certain amount of friction, just like that. Okay? So, when we want to know what's happening, all right, first thing we have to do is to identify all of our forces, and then we've got to transfer all of those to our free body diagram. So, this guy right here is our FBD. There's our free body diagram. Okay? And that's very useful. And so we could see from the free body diagram, if we were going to start to try to analyze things, we would see that in terms of what is here to the right, it has to be balanced by what is here to the left. What is down below has to be balanced by the normal force plus Ty. Okay? And so our free body diagram gives us the tools to be able to look at what's happening horizontally, what's happening vertically in any given situation. Okay, so let's look at another case. All right, so we've got this child, and let's suppose it's an equilibrium situation, and the child's going to be sliding down just like this. And so let's think about what's happening with the forces. All right, so we'll start with the low-hanging fruit. So literally the gravity. Here's the child's weight, just like this. Now let's think about normal forces. That's usually good to hit second. And so our normal force is going to be this way. Okay, because it has to be at a right angle to the surface. So the surface of the slide is here. So our normal, our right angle is going to be on it right here, just like this. Okay, so that normal is acting there on her bum. Now, we could break it down and we could say how much normal is on her bum, how much is on her thighs, how much is on her calves, how much is on her feet. But we don't care. We don't need to break it down that much. We could think about the total effect where the slide is pushing her, keeping her from falling down through the surface. If you didn't have a normal force, then the child would just sort of sink right through the slide, and that would be kind of weird. And because the normal force is at that angle, you can see what the result is she's going to end up being pushed this way here because the normal force and the weight are working together to push her that way. Okay. All right. Now we're also going to have some friction And the friction is going to be back this direction here. So there's our friction acting on the little girl. Okay. Now, we could draw our free body diagram like this. We can have our weight in here, and we could have our normal force here, and then we could have our friction here. Okay. Now, if we do that, then I've got to break my normal force into X and Y components, and I have to break my friction into X and Y components. Okay. We could do that. That's fine. That's fine. But turns out there is no rule that says your Cartesian coordinate system has to be this way. We could tilt that sucker. All right. And that's what we've got there. I've drawn a tilted coordinate system for you. Now, if we do that and we draw in our weight, it's here, which might seem a little bit odd, but look what happens with our other forces. Here's my normal force, and it's entirely in the direction of Y. And then here's my friction, and it's entirely in the direction of X. Just like that. So the only components I have to worry about is my weight. Okay, is my weight. Now, so let's go ahead and get those components. All right, so here is my X component. All right, now I don't like calling it an X component because usually we think X is straight to the right. So I'm going to call it my parallel component. So it's the parallel component of my weight, just like that. And then down here, I've got this component along Y. That I'm going to call my perpendicular component. Okay. All right. Now, if we know, I need a new color. Yeah, we'll make it work here. If we know that the angle of my slide here is an angle theta, then that means over here, this is an angle theta. Okay, so I've got a right triangle here, just like this. Okay, and that means then if I've got a right triangle over here also, what I'm trying to get at is that this angle right here is also theta. Okay, so pause the video, work through that, convince yourself that if we know this angle is theta, then that angle inside there is also theta. Okay, that's pretty important. Okay, so I'm going to get rid of those. Now, the reason I'm bringing this up is because with that angle theta right there, that means if I'm interested in my component, my parallel component, that's actually W sine theta. And my perpendicular component becomes W cosine theta. All right. You want to memorize that result. All right. If we've got a ramp and it's got an angle on it, okay, then you need to just automatically know, oh, the parallel component for my weight is W sine theta. The perpendicular component for my weight is W cosine theta. Okay. You don't want to have to stop and work through the geometry every time you run into this. Okay. Just plop that away in your head. Okay. Now the weight is actually mg. And so we could write that in here as mg sine theta. And this guy could be mg cosine theta. Okay. So just commit that to memory. You're going to save yourself a lot of trouble. Okay. All right. Now let's look at a free body diagram that's going to be a little more interesting. Okay. So we've got a rock climber. Okay. Now what I'd like for you to do is pause the video here and see if you can figure out what are all the different forces that are acting on her. Okay. So pause the video, and then when you got a good idea, then come back to it. Okay. All right. So I hope you did it. So let's get her weight. Now she's at an angle. So I'm going to kind of put this at her approximate center of mass, which is going to be right there. So there's her weight, just like that. All right. There is a rope here providing some tension, and it seems to be straight down. Okay. So for our purposes, we'll just assume it's straight down. Okay. So there's a tension on her there. By the way, this is that's a W right there. Okay. Now, where does she have some contact? Well, she's got some contact with her foot, but that contact, the force from the contact is our normal force. It's got to be straight out from the surface, which means it's actually here. So let's call that N1. And then she's gripping this thing, and it's going to be here, N2. Just like that. All right. So now let's go back in and throw in some friction. Okay, let's start with her foot. She wants to, her body wants to slide down. So the friction is going to oppose the relative motion between her shoe and the rock to provide an upward force that has to be at a right angle to the friction. So I'm going to call that F1. And then same thing up above. Okay. And so she's going to get a little bit right here. We'll call that F2. Okay. So the normal force and the friction are always going to be at right angles to each other. That's always going to be the way that works. So if we shift all this to our free body diagram, all right, so we've got weight here. We're going to have whatever the tension is. So I'm going to just kind of assume it's less. Okay, now I've got my two normal forces, so I'm going to put one of them right here. There's one, and of course it's going to have an X and a Y component. And then I've got N2, and my N2 is, I don't know, maybe something like that. That might be too much of an angle on that. I don't like that. Let's change that up. It may be a little more like this. There's my N2. Then I got my friction, so F1 is over here, and then F2 is going to be just a little slightly different angle, F2, like that. In my drawing, it looks like it's going straight up. It should be tilted just a little bit. Okay. All right, so then I'm in great shape to do my analysis. I want to split N1 into X and Y components. I want to split N2 into X and Y components. F1 into X and Y components, F2 into X and Y components. Okay, those sorts of things like that. All right. Okay, now just sort of what's kind of interesting there is, she's pulling with her hand grip on the rock there. Okay, and then there's a contact force pulling back, and that helps hold her body up. Okay, but the result of N2 actually makes N1 have to be bigger, all right, because N2 is pulling slightly in the negative X direction. The only thing pulling in the positive X direction is N1, all right? So the more she pulls, the more N2 she gets, which means the more N1 has to happen, okay? And it turns out that her friction, F1, which is holding her up, depends on N1. So the stronger she makes N1, the more F1 she gets. Okay. And so we kind of in our mind's eye, we imagine N2 is keeping her from falling backwards. And it is doing that. But N2 is also causing more N1, which causes more F1, which helps her stay on the rock because of the friction. Okay. Kind of fun. There we go. Anyway, so there is a nice juicy one. Okay. But in all three of these, hopefully you can see we've done the same kind of thing as we started out, trying to figure out what forces do we have. Okay, and it works out great to start with the weight, then go to normal forces, then go to tensions, and then go to friction at the very end, just like that. And once you've identified all your forces, then you're going to transfer them to your diagram. This case is complicated enough. Tilting our coordinate system one way or another doesn't make any difference. It's just going to be messy. Okay, just enjoy the mess. Like a toddler with a can of SpaghettiOs. Just enjoy the mess. All right, there we go.